So the first definition is a conservative vector field. A vector field is conservative if it is a gradient of some scalar function. And that's like saying the derivative of little f is equal to big F, the gradient field. And if you have your original capital F function, vector field F, capital F, and then you know that it's a conservative vector field, then we can find somehow, we can find a little f so that the gradient of little f is equal to the original gradient field, conservative vector field. And that little f is called, little f is the one that we're calling a potential function. That's a potential function. And so this is the statement of the theorem here that says the integral of a derivative of f is equal to the original function f evaluated at the boundary. So I think I said endpoints last time. So this time I'll say boundary. So what did I say? I said the integral of a derivative is equal to the original function evaluated at the boundary. Still the same, right? Essentially saying the same thing. Because the endpoints turn out to be the boundary of a curve. So I want to use this term boundary because now this statement will resonate through the rest of the semester when we discover more, quote, fundamental theorems of things. So just like the fundamental theorem of calculus, this is a theorem that relates derivatives and integrals and something with boundaries. All right, let's do an example. I don't think we've done this particular one yet. I just dug this one out from the homework. And this is in 3 dimensions. So let's look at this in 3 dimensions. Let's first do this. Say we don't know that F, capital F here is conservative. We don't know if it's a conservative field. There's a way to check. I think there was a way to check in 2 dimensions, but we don't have a way to check in 3 dimensions yet. And so let's say for now, we don't know if it's a conservative vector field. We're not going to check if it's a conservative vector field. Let's just go at it and compute the line integral. Conservative means that it's a gradient field. So a conservative vector field means it's a gradient field, which means F, for capital F vector field F, there is some little f so that it's the gradient of that little f. All right, so let's first just compute the line integral. And then once we compute the line integral, let's dig deeper and see that it is actually a conservative field, or at least I think it is. And then we'll find another way to approach this particular problem. This is in 3 dimensions. We're going to need to construct a line segment from 1, 0, negative 2 to 6, 5, positive 2. And since it is a line integral, the direction will matter. It is important that we go from one to the other. So we need to find a couple of things. We need to parameterize C. C is what we're C is what C is that curve, that line segment. We have the vector field, and in our parameterizing C, we can figure out what ds is going to equal to. So remember the working definition of a line integral. It is an integral from a to b of capital F evaluated at r of t, dotted with r prime of t dt. Now there are ways to shortcut this if you want. We can spread this out with a dx, dy, dz integral or differentials or whatever you want to call it, if we want to approach it that way. But I like to approach it this way when we're parameterizing things. So let us parameterize this line segment first. So the parameterization for C has three components, x, y, and a z. And we can parameterize by finding the vector connecting these two. So that vector is 6 minus 1, 5 minus 0, and 2 minus negative 2. So that's your direction vector for your line segment. And so it's going to be the first point plus t times the direction, and then we should be able to write that as 1, 0, negative 2 plus t times 5, t times 5 for the second one, and t times 4. So our x looks like it's 1 plus 5t, our y is equal to 5t, and our z is equal to negative 2 plus 4t. Okay? Now we want to find the differentials, the derivatives of these things to find r prime of t. So let's find x prime, y prime, and z prime. And because this is a line segment, it shouldn't be too hard. You have 5 dt for the first one, 5 dt for the second one, and 4 dt for the third one. Okay, so the only thing left to do is to insert our x's, our y's, and our z's into our vector field. And so let's begin to set up our integral. By the way, this is a line segment parameterization. So our line segment parameterization is going from 0 to 1, the way we have it set up. So the vector field evaluated at y and z in the I direction, so that's 5t, and z is minus 2 plus 4t. That's the first component of the vector field. The second component is x times z, so that's 1 plus 5t, and then the z is minus 2 plus 4t. And then the last component is x times z, so x and z, xy plus 8z. So xy is 1 plus 5t, y is 5t, plus 8 times z, negative 2, plus 4t. So those are your components for your vector field. You're going to dot that with 5, 5, and 4. And they all have a dt attached to them. So simplify, multiply, and this is not going to be more than a second degree polynomial, so we should be able to do this easily, right? All right, so I guess this would be an opportunity to show you how to use your graphing calculator to find integrals really quickly. So let's do that. Just so the people with the TI-84 have never done this don't get left behind with finding and computing integrals. And so your calculator can only compute regular single integrals, it doesn't know how to deal with line integrals. You can't put in a line or a path integral. You have to take your line integral or path integral and make it look like an integral that you can integrate in Calc 2. So without doing much simplifying, I'm going to need to just type in the function. And for the TI-84, you only have x as your variable for this. So we're going to change everything into an x. So I have 5 times the first component. So I'll just type it in as about as raw as it can get. So that's the first component, and then I have the second component, 5 times 1 plus 5, 1 plus 5t, we'll call it x. And then I have a minus. Don't forget that your negative sign and your minus signs are 2 different buttons in your calculator. Minus 2 plus 4x. And then the last component, you have to be extra careful with parentheses because you have 2 terms in your vector field. So I have 4 times, and I'll put a big parentheses, and then start my first 2 with a smaller parentheses. 1 plus 5x, that's the first one. The second one is 5x. And then now this is where your terms come up. And then the positive 8 times, and then another negative 2 plus 4x. So close that first parentheses and close the big parentheses.
You need a plus between your basically your first, your second term and your third term.
Oh.
There's a 4 after your 4x.
Right here.
Yeah.
Thanks. Insert plus. Well, I think that's it. You got us a nice function here. Say it again? I don't know. Yeah, that could be a problem. So primitive to use a calculator, huh? Back in the old days, I used to use a calculator. So this is the function, and then we can just zoom fit. We know that we have to get through 0 and 1, so you can adjust your window already to make sure it includes 0 and 1. But if I just zoom fit, that would be zoom and z fit. Eight, maybe 0. So if I zoom fit it, I can get an idea of how high these things will get, although I really don't care about how this thing looks like anyways. I just care about the integral. All right, so to actually integrate, there's a trace button, and right above it is calc. So that's what we want to do, is second function and trace, or calc. And we want to hit 7 for the integral. And it's going to ask us for the lower limit. And I don't know if this is going to include 0, but I'm just going to type 0 in for your lower limit. Enter. Nope. So it looks like my window does not include 0. So let's click on window to make sure it has 0. I think if I go -1 here, to x max, I don't need to go all the way up to 23. Let's just go to 4. And then it looks like the y max and min looks like it's huge, so I'll just leave that alone. And let's try it again. lower limit, let's try 0, enter, upper limit, let's put 1, enter. I can't see it, but the answer is 60. Well, that was a pain. So your integral is equal to 60. Okay? Now for my fancy calculator, I have a line integral in 3 dimensions. My vector field is yz, xz, yx. Oh, did I remember I remember to put the z there, right? 8z. And my r of t is a line segment from 1, 0, -2 to 6, 5, 2. And my integral's from 0 to 1. And then the result is still 60. That was a little maybe overkill for this, huh? In any case, our integral is equal to 60. All right? Yeah. Graphing in 3 dimensions, I think, would be, I don't know how useful it would be, but sure, just for you. So we need to plot this vector in 3 dimensions. What was it again? It was this vector. I don't know if we're going to see anything too revealing graphing it like this. We want to include our x values. Our x is 1 and 6, so I think we can let our x go from 0 to 7. Our y value goes from 0 to 5, so let's go 0 to 7 for that too. And our z value needs to include -2, so for that I'm going to go from maybe -3 to 3. So we have a 3-dimensional vector plot that looks like this. Let's throw the line in there somehow. And the line is a parametric plot. Should have just did this in a graphing calculator. Maybe we want to exaggerate the points also. And then the points where at point was that 1, 0, -2. And 6, 5, 2. All right, let's see if it plots. Nope, didn't plot. Nope, didn't plot. One more try. There it goes. So this is a graph. I don't know how useful it is, but essentially we're doing some calculations on the work. You can think about it as the work being done. Since it's a straight line, it just goes from one point to the other, and then you're taking dot products of that line with each vector that's passing through there from the vector field. So I don't know if it's too telling, but it's just there. Okay. So that's the graphics of that, and what we want to actually look at is, and it's hard to tell also just by looking at the vector field itself, especially in 3 dimensions, that if this is in fact a gradient field, a conservative field, then we could have done this problem in a lot easier way instead of doing that thing that we just did. So I guess the question was, is F a conservative field? So if it is, then we find a potential function. And we'll find a way to check that F is actually a conservative vector field. But for now, let's just assume yes. Assume. Because I said so. But the actual basis for that we'll see. Maybe by the end of this class, but for sure in a couple lectures from now. So assume that it is. So we dealt with a conservative vector field. That if the answer is yes, we can find the potential. Let's use those fancy words that we just learned. So the potential function we'll call little f with no arrows, is not bold-faced. And that means that if f is a potential function of capital F, then capital F is equal to the gradient of little f, which means that each of these components must have come from your little f by taking the derivatives. That means the first component must have been the derivative of little f with respect to x. The second component must have been the derivative of little f with respect to y. And then the last component must have been the derivative of little f with respect to z. So we will find out if this is in fact a potential function. So let's assume that the yz, the first component of the vector field, was a derivative of little f with respect to x. So if we were going to try to attain the original function little f, we need to find the antiderivative of xz, of yz with respect to x. And we do that, yz is a constant with respect to x, so this is just going to be yz times x. And then we assume also that if we took the derivative of your original function with respect to x, then everything else with a y and a z would have been constants. So you might have some terms with a y and a z in it that don't have an x that might have disappeared when you took the derivative with respect to x. And so we have this as our function, potentially. So we take the second component and take the antiderivative of that with respect to y. So that's xz with respect to y. Xz is constant, so it's just going to be xz times y. Plus another possibility of a function with respect to x and z, because x and z are constants. And so I think I was doing this before. Maybe I should be a little bit more formal on this. These two things are different constant functions. And I say constant functions, it's kind of weird, but it's a function that's constant with respect to y. It's a function that's constant with respect to x. So I'll put C1, C2 because they're most likely going to be different. And we were done with this last time with just two components, but now we have a third component, so we need to consider the third component as well. And that is xy plus 8z now with respect to z. And so the first term is going to be xyz again, so we know that that's a good sign. I'm going to have all that. And then the antiderivative of 8z is z squared over 2, so to cancel the 8, cuts it in half. And now you want to allow for another function with respect to x and y that is constant to z. And by inspection, you can see that your function would be made up of x, y, z, and then there's a 4z squared here that probably would have lived in C1 and C2. And then C3 didn't have any extra, so that must be it. So we can probably conclude that our function f of x, y, z, little f, is our potential function, and that is x, y, z plus 4z squared, and plus another, now it's a real constant with no x, y's, or z's, just a constant. But we won't need that because, you know, just like in integrating, if we do the antiderivative, you have a plus c, but if we do the definite integral, the plus c's disappear the same way it's going to disappear here. And if you want, take the gradient of little f, you should get the vector field. Okay? All right, so now that we have the potential function, we know that this is in fact the conservative vector field. And this is the capital F is the conservative vector field, and capital F is a gradient field. It's a gradient of this. Then by the fundamental theorem of line integrals, we know that if we're going to take the line integral of the gradient field, that this is simply equal to the gradient field, no, not the gradient, the original function, evaluated at the endpoints. Evaluated at the what? At the boundary. That's our new term now. It's the new style. Evaluated at the boundaries. So the boundary was from where to where? Okay, so we have to use the endpoint, the B endpoint first, right? So this is your B, this is your A. So we have to use the B first, and that's 6, 5, 2. And then the starting point is 1, 0, negative 2. And so we simply put that into our equation. Oh, that gets big. 6 times 5 is 30 times 2 is 60. Minus z squared is 4 times 4 is 16. And then, so that's the first one. And then we put 1, 0, negative 2. I guess that first term is going to be 0, 1, 0, negative 2, positive, negative, positive. What? 16. Positive or negative? Positive 16. Oh, this should be positive also, right? Yeah. So we got 16 minus 16 is gone, so this is equal to 60. So we got the same result as what we got in our line integral, as we should expect, because this is the shorter way of doing it. So you're finding the antiderivative. Okay? Questions? Yes? The force is a vector field, yeah.
Acceleration would also be a vector field?
I don't think so. Yeah, maybe acceleration, because it's depending on what it is. I'm thinking of our standard gravities. Your acceleration, it pulls down, so it could be a vector field. It's just pulling down.
Those kinematic equations, does velocity like a potential function?
Damn, Caesar, you're making me think too hard. I'll have to say I don't know for that one, and I'll get back to you, maybe. I think there's some parallels to that, but it wouldn't, the way we studied our motion, equations of motion before our first exam, I think that's treated a little bit differently, because it's the work and force applied to things, and so it's a little bit different from just watching the path and finding out the path functions. So I don't know, but I'll try to research that. Any other questions? Easy questions? Oh yeah, all right. Yeah, we put 6 in for x and 5 in for y and z in 2 in for z, and then we calculated it here, and then we got this for the first one, and then this for the second one, and then we got it to equal to 60, which is our answer from the previous page. So, by the way, because this is path independent, we actually did our computation going from this point to this point in a straight line. According to this theorem, if you decide to not go in a straight line, but you're still starting at the same point and ending at the same point, that you should still get the same answer. And that means any other path, as long as you start at the same place and end at the same place, or not the same place, then you should get the same answer. Okay, regardless of what path you're taking. All right? So that leads us to another idea called path independence. So this is a definition of path independence, that if you're path independent, then it doesn't matter what path you're taking, right? So whether you're going in a straight path, a straight line path, a semicircle path, or a path that loops around in different places, as long as the direction is going from one place to another, then it's still going to give you the same answer, the same line integral. So all these different paths will give you the same result for your line integrals. Okay? So line integrals are conservative vector fields line integrals of conservative vector fields are path independent. And they're all saying the same thing, essentially. But if you notice, something interesting about path independence is that, somebody brought this up last time, that if you're starting and ending in the same place, what's that going to be? It's going to have to be 0, because just by the fundamental theorem of line integrals. Those, if it's path independent, we have a conservative vector field, and then there's a potential function. And so if we just translate this into the fundamental theorem of line integrals, this is going to be equal to the function evaluated at one endpoint minus the function evaluated at the other endpoint. But if these two endpoints are the same, then a result is going to be, we're subtracting the same values, which is going to be 0. So what we're doing here is essentially building a bunch of equivalencies to say that if something is a conservative field, then it's a gradient field, then there's a potential function, then the path of a closed path, the line integral of a closed path is going to be 0, and a bunch of other things that we can say all together. I wonder if we can just all say it at once. What else is there to say? Vector field, then F is conservative, then there exists a potential. Oh, we already know that. Oh, this one. For something that's two-dimensional vector field, we found that the mixed order partials are equal, right? So this is the theorem associated with that. So if F is a conservative vector field, then F is actually the gradient of little f, some potential function. That means F is actually can be seen as Fx comma Fy as your P and Q functions, right? So that means if this is a nice function, that means we could take the derivative of this thing with respect to y and then take the derivative of this thing with respect to x to get those mixed partials. And then they're supposed to be equal to each other. So the derivative of fx with respect to y should equal to the derivative of fy with respect to x. Okay? So that's really what's happening over here. Instead of fx and fy, instead we're going to call it p and q. And then taking the derivative of p with respect to y, and taking the derivative of the second one, q, with respect to x, should be equal to each other. And so that's the relationship that we can check for to see if this is a conservative vector field. So if we have something that's two-dimensional, all we have to do is take the partial of the first one with respect to y, take the partial of the second one with respect to x, and if they are indeed equal to each other, then we can conclude that this is a conservative vector field. Okay? If they're not equal to each other, then, well, it's not a conservative vector field. Then you can't use the fundamental theorem of line integrals. Okay. So that mixed order partials, well, we call it mixed order from the potential function, but in terms of the vector field itself, the P and Q partials are equal to each other. Notice the subscript of P, right? And the subscript of Q. I mean, when I say subscript, it's the derivative with respect to. So derivative of P with respect to Y, and then the derivative of Q with respect to X. Okay, so that's another way of check. We still don't have a way to check with 3 dimensions until next time. Okay, so all these theorems are really saying this thing. I have a nicer version of it here. So this is your big grand summary of these conservative functions for 2 dimensions. So if you find that your vector field or your integral satisfies one of these conditions, then you can say everything else in this list about the vector field of the integral. So that's saying that f is conservative, then f is a gradient field, then there's a potential function, then that means it's path independent, which means you can use the fundamental theorem of line integrals. And if C is closed, then it's equal to 0, your integral is equal to 0, and that is based on this bottom function over here, or the bottom relation. Okay? All right, questions? So there's this interesting, yeah, oh.
Not all functions have second order derivatives where fxy equals fyx.
Correct.
So how does this apply there?
It doesn't. So if these derivatives are not equal to each other, then that means you don't have a conservative vector field, and you can't find your potential function. So you'll have to do your line integral the old-fashioned way until you come up with more interesting theorems.
Do we have to come up with that, or are they just in other textbooks?
Of course they're in the textbook. So we'll see one of them tomorrow. Mr. Green. Okay. There was a quiz that I was going to give you instead of the one that I just made up. No, I wasn't going to give it to you now. And I don't know if I was going to give it to you for extra credit, but I was... It was a not used quiz. There's a quiz that looks something like this. We have a we have a magnetic field. Now,
I know what I'm doing.
this actually should be seen in 3 dimensions, but we're going to look at this from a 2-dimensional point of view. This is a magnetic field that works around. If you have a rod, with the wires wrapped around, you create a magnetic field. And then there's this is a vector field that goes around, but only seen in 2 dimensions. And I don't know if this vector field looks familiar, but it's a minus x in the x, or minus y in the x component, and then a positive x in the y component. But this is being divided by the square root of x squared plus y squared. So it's doing something to the length of this vector field, or the length of the arrows that we're looking at. Anyways, this vector field or something similar to this is also in, I don't know if it made it to your homework problem set. I don't think it did, but it was one of the questions in the book. But here's a couple of quick questions. So this is why I kind of backed off and decided not to give this to you, because there was no room for you to do your work here. It had so many questions. And so I thought maybe I'll set this up a little bit differently. So instead, maybe let's take a look at it here and see how quickly we can do this.
Yeah, can you make this
Nah. So here's your vector field. And here it says determine this thing, because we're going to eventually want the line integral. And so part of computing the line integral, sometimes you want to figure out what the integrand looks like. They want us to figure out what this integrand looks like before you throw it into the line integral, before you integrate it, essentially. So if you have a radial line from this vector field, and a radial line and goes through the origin, that's what a radial line is, then we want to figure out what this is equal to. So we want to figure out what x and y are. And the easiest thing for x, remember, for something like this is for a function, you can just let x equal to the parameter t, and your y is going to be whatever that thing is evaluated at t. And so given this, your dx is equal to 1 dt, and then your dy is equal to m dt. And so we put all that information here. We're going to see that b dotted with dr, or ds, or rs, whatever that is some constant. Let's just call this constant c, times negative mt comma t, I guess we'll use the I and j, plus tj divided by t squared plus mt squared. And then we dot this with r prime of t, the derivative of these things. And so we'll see that if we just focus on the dot product here, we have minus mt times 1 plus 1 times m. Oh, where's the t? Oh, there's a t in there. So if we just take that dot product, we're going to get mt, negative mt plus mt, which is equal to 0, right? So it turns out that this is equal to 0 before you even integrate. So anytime you try to integrate this over a line segment, you're going to get 0. Okay? All right, so that's the first one. The second one is parameterizing this thing with a circle, and x squared plus y squared have circle properties and stuff like that. And this one's not going to be 0. We're out of time. Should we finish? Let me do a couple more steps here. So cosine t and sine t. So the derivative is minus a sine t dt, and y is going to be a cosine t dt. And then when we put that into the b dot r dot dr equation, we're going to have that constant again. You have x squared plus y squared in the denominator, and then you have minus y minus a sine t in the x component, and then positive a cosine t in the j component. And then we dot that with with minus a sine t, positive a cosine t. And then we're going to, when we take the dot product, we're going to get negative a sine t, negative a sine t, so that's a squared sine squared t. And then a cosine, a squared cosine t. So this is just a constant because all the t's are gone. So you have that constant c, you have a squared and a squared, so that's just that constant u sub 0 I over 2 pi. So, we're assuming that it's we're assuming that it's a counterclockwise direction. So if we ever have to parameterize in the clockwise direction, we just throw a negative sign. So this is your b, and then you just need to put in the limits. Okay. So I'll put this online. I'll put this worksheet online for you guys to mess around with it. I don't think I'm going to give it as extra credit. I think there's too much extra credit flying around already, and you don't need that much extra credit. Some people do need. Anyways, we'll think. And have your test. Yeah. Yeah.